Okay, welcome to Monday Morning Methane, where we are making Monday magnificent, not again for the first time. Today, I want to get into some satellite data that came out of Francis Royland's recent master's thesis, which was recently published online. First thing I'm going to say before getting into this, talking about the detection performance of satellites in controlled release testing, is that Francis is the expert, not me. And so there's a meta seminar on this exact topic that goes way more into detail. And of course, reading the thesis is going even further. So I recommend getting into those, and I'll post the links in the comments. So what happened here in this research? The University of Stanford has a controlled release facility where they're able to release methane emissions at a broad range of known rates and then evaluate the performance of different satellites. The interesting thing about the commercial and nonprofit satellite landscape right now is that you have instruments in space that are capable of detecting and quantifying emissions. But then you have both publicly available data and private organizations who collect their own data and sell it. And for the publicly available data, you have companies who are providing services of analyzing that data. And so you have different algorithms, different vendors who are analyzing publicly available data and saying different things about it. And so this paper kind of gets into evaluating the performance of each of those. So the first thing, we're just going to talk about detection today. I don't want to get into a quantification because it's a whole other ball of wax. But this figure is a really fantastic way of demonstrating how each of these different satellites answer the question of how low can you go? We talk about minimum detection limits. More commonly, we talk about probability of detection. The two kind of ways of thinking about this in this figure are the partial detection range and the whole release range. And so when you look at these different bars, forget the dots for the moment. The bars illustrate in pink areas where the researchers have found the satellite may or may not detect an emission. And the gray indicates regions where the satellite is very likely, if not highly probable, that a detection will occur if an emission is at that rate. And so you can see on the x-axis here, you can see the ranges of emissions that were conducted for the controlled release testing. It looks like some of the emissions were as low as around 50 kilograms per hour, ranging all the way up to just over 1,000. And on the y-axis, you can see the different satellites and their performance. And so there's a few things to point out here. One is that different satellites were tested under different controlled release data. And so not all satellites were present and imaging under all releases. And that's what these black dots are. And so a couple of things to point out here. One is that some satellites, you may only see one or a small number of black dots. In those instances, it's really hard to evaluate much. You only have really one test or a couple of tests. It's hard to say something conclusive with such a small sample size. The other thing to notice is that different satellites detected over different emission rate ranges. And so if you look at GHGSat, you can see that they pushed really hard into the lower release rates, whereas some of the other satellites did not, and rather were evaluated for during larger release events. So when we look at this, there's a couple of things to point out. One is that some of these satellites performed very, very well at relatively low release rates. We can see that in particular for GHGSat, for Tanager, for Worldview 3, we have detection capabilities extending in some cases below 100 kilograms per hour for the partial detection range. Remember, that's not for a 90% plus confidence of detection. But even for even those partial detection ranges for those three satellites are relatively narrow. And at say 100 kilograms per hour for some of these, they are confidently detecting emissions. Keep in mind, especially for Worldview 3, there's only a sample size of around 5 for this phase of the study. Tanager, there's a few more. GHGSat, there's a lot more data, so more robust results, especially for those lower releases. So this gives an idea of how satellites are performing, where we have good data, where we have less good data. I anticipate that Stanford is going to continue these releases, as they have an autonomous system set up for performing these releases now, which makes it easier. I think our director of R&D, when he was participating in some of these studies, was living in the desert, making it a little bit more difficult. The next question we're going to look at is how different satellites and different teams performed. But the first thing to point out is, I just highlighted this text, is that in this phase, there were a total of 571 responses recorded. And of these, 132 were filtered, mostly due to clouds. And so these were instances where it was not possible for the team to make a determination. And so remaining of those were 439 non-filtered responses. And of those, 186 were true positives, which means that there was an emission, and the team said there was an emission. 138 were true negatives, which means there was not an emission, and the team said correctly that there was not an emission. And the remainder were false negatives and false positives. So this is when the teams got it wrong. And so for the images where they were able to make a determination in aggregate, and so obviously the performance changes depending on the company and on the team, but in aggregate, there was a 73% chance of getting the detection determination correct. Okay, so now we're going to dive just quickly into some of the individual satellites and the teams. I'm just going to walk you through this because it's kind of a lot. Each plot is a satellite, and then the columns are the teams. And so for Nmap and Prisma, you have lots of different teams who are applying their algorithms, applying their methodologies to the satellite data. For others, proprietary data, for example, GHGSat, Tanager, you only have one team, and so you only see one bar here. So we're going to start up here with Nmap and Prisma. The dark green bar, this is good. This is what you want to see. The light green bar, this is good. This is what you want to see. So the dark green bar means that a true positive. There was an emission event, and it was detected. So the determination was there was indeed an emission event. The light green bar was that there was not an emission, and so the controlled release team at Stanford did not release anything, and the satellite correctly inferred that there was no methane there. The orange and the red are where you start having problems. So the orange bar means that there's a false negative. That means that there was emissions present, but that the team was not able to detect them. And then the red bar is a false positive. This means that there was no emissions present, but that the team said there was. This can often happen in some cases if you mistake a cloud for an emission plume. But in general, what we see here is that these results are really good. There's a lot of green. The gray bars are where there was the satellite was not tasked. There was no imagery, so impossible to say for those. As we dive into Sentinel-2 and Landsat, we see a very different story. And so the first thing we notice that the dark green bars are far fewer, far lower. And so these again are the ones where there was an emission present, and the team was able to say that that there was indeed an emission present. One thing that's also important to notice here is that there's a lot more variability between the teams. If we go back to the Nmap and Prisma satellites, the teams are pretty consistent. So it basically means it doesn't matter who you hire, you're likely to more or less get the same result, unless you hire Team H from Prisma. Don't hire Team H. But if you look at these results for Sentinel-2 and Landsat, you see that there's quite a lot of variability between the teams, especially in terms of getting it wrong. And so all the teams are getting it wrong more in terms of having more false positives and more false negatives. But some of the teams are getting it more wrong more often than the other teams. And some teams aren't detecting anything. So, for example, Team D and H for Sentinel and Team H for Landsat wasn't able to infer any true positives, whereas Team J was able to infer quite a few, almost 50% of all of the events. And they were right the majority of the time that they made a determination. So you can go through for many of the other results here. And I think that's most of what I'm going to get into here today. There's quite a lot of variability, both in terms of the detection thresholds, the confidence with which one can say that a detection occurred or not, and overall performance. There's obviously a lot more to get into this thesis. Francis has done an incredible job here, and the team at Stanford. This is invaluable data for anyone working in methane emissions and thinking about how satellite data can be leveraged. A big takeaway for me is just how much satellite data has improved over the years. I remember quite a long time ago having conversations. Actually, we attended the controlled release testing in Stanford's methane monitoring challenge, I believe, during my PhD almost 10 years ago. And I remember having dinner with a gentleman who said, satellites are in the 1,000 kilogram per hour detection range right now, and it's just physically impossible for them to get any better. And at the time, that guy was a physicist, and so I believed him, but I didn't realize just how wrong he would be. And so it's been super encouraging to see this innovation, and really excited for it to continue. So thanks for tuning in. If you have any questions about this thesis, don't ask me. Francis is the one who's done all the incredible work here. And I'll make sure to post the link to the thesis in the comments. I don't think the meta talk is available online yet, but keep your eyes out for it. Thanks for tuning in. If you are a fan of Monday Morning Methane, please like this video. It helps helps for LinkedIn circulation. And then you can click on the hashtag. I think this is the 8th edition of Monday Morning Methane, and so you can go and watch all the previous videos as well. Thanks so much for tuning in, and have a wonderful rest of your week.